Okay, hello everyone. Welcome to our session today. And today we will have three speakers from China. And each speaker will have 20 minutes for their talk. And I will remind the speaker 5 minutes before the end. So please control the time. And let us welcome our first speaker, Dr. Han Wang from China Agricultural University. Her talk is about transcriptome-wide association studies using nonparametric Bayesian methods to integrate multiple functional annotations. Okay, let me give time to Dr. Wang.
Thanks for your kind introduction. And hello, everyone. My name is Han Wang, and today I'm very happy to be here to share my research with you. And my topic today is about the transcriptome-wide association study, which in short we call it TWAS. And here I want to introduce our new non-parametric Bayesian framework for incorporating multiple annotations in the TWAS framework. And as we all know that the GWAS study has successfully identified thousands of genetic risk loci for complex traits. But unfortunately, the majority of these loci are located within the non-coding regions and whose molecular mechanisms remains unknown. So about 10 years ago, the researchers have proposed to the TWAS framework, which build a bridge between the SNP and the phenotype we are interested in, using a mediator gene expression. And the main assumption behind the TWAS is that the genetically regulated gene expression, which we call the GREX, might play a key role in explaining the etiology of the complex traits. And since the traditional TWAS mainly consists of two steps, the first step is we call it an imputation step. For example, as shown in this figure, if we have a large cohort, for example, the GTEx database or the RoseMap database, where for each individual, we have its genotype information and its gene expression information for each gene G. Then we can use a very simple linear regression model to establish a linear relationship between the genotype information and the gene expression information. And then we can obtain an estimator of the coefficient omega hat. And if a new GWAS dataset is available, for example, in this figure, and in the left-hand side, if a new GWAS data is in hand, then we can use the omega hat obtained in the first step to impute its gene expression level by using this simple formula. Here, X new denote the genotype information for this new GWAS dataset. And then we can get a GRES hat. And the second step of the TWAS is called the association step. And if the individual level data is available, the main goal of this association step is to test whether the imputed GREX has a relationship with the phenotype of interest, or from our statistical perspective, our main goal is to conduct a hypothesis testing to test whether this coefficient beta is equal to 0 or not. So in reality, not all the GWAS data are individual level, but we only have summary level data available. So and thanks to some fantastic researches, for example, this Nature Genetics paper or this Nature Communication paper, even if we only have summary level data set, we can also construct a test statistic to help us conduct this hypothesis testing. Since the original TWAS has been proposed, there are plenty of other TWAS works have been and the main logic behind this TWAS work is that the more accurate imputed gene expression level will induce a higher power of TWAS study. One important line of this work is to do the data integration, or we incorporate the annotation information, for example, the epigenetic information or the 3D genomic data information, to help us do the the imputation step and get a better omega hat in the first step. For example, in this 2020 paper, the authors use a roadmap data set which they extract the epigenetic information to help us establish a more powerful imputation step. For example, for the cis-SNP-K, we assume that this cis-SNP-K's effect size on the gene expression EG is denoted as omega K, and they impose a spike and slab prior on this omega K, and the probability that this SNP-K has an effect on the gene expression is equal to pi K. And how do they connect this probability pi K with the annotation information? They use this formula. So the rationale behind this formula is that the larger the annotation score of this SNP-K, then we have a larger probability to say that this SNP-K might have a greater effect size on the gene expression. And here is another work which incorporated the epigenetic information into the TVAS framework. And the authors adopted adaptive lasso like penalty to incorporate the roadmap epigenetic information into the TVAS framework. And here for this 2022 Nature Communication paper, besides using the epigenetic information, the authors also use 3D genomic information to incorporate into the first imputation step. And our work is motivated by a new database called the FAVOR, which is a database developed by Sihoni's group from Howard University. And as you can see from the from this figure, besides the epigenetic annotation information, there are also plenty of other types of information. For example, the protein function, the distance to coding, and the conservation annotation information, which we can utilize to incorporate into the TVAS framework. But under this framework, when multiple annotations are considered, the assumption that when annotation scores increases, the effect size will increase might be violated. So in this case, we must construct a new model beyond the linear assumption to help us more effectively incorporate so many more annotations into the TVAS framework. So before we get into the details of our model, let me introduce a very fantastic TVAS method called Tiger, published in AJHG in 2019. And they, in the first imputation step, they also assume a linear relationship between the gene's genotype information and its gene expression information, but they impose a Dirichlet process prior on this effect size vector omega. And the rationale behind this Dirichlet process is that they partition the effect size vector into infinite many clusters. And within each cluster, for example, if we assume that the effect size of omega of SNP-K belongs to cluster J, then its effect size follows from a normal distribution with mean equal to 0 and the variance equal to sigma j. And here is our MET model. Our MET here stands for multiple annotations associated TVAS. And in the our main change is about the imputation step. We also assume that there is a linear relationship between the genotype matrix and the gene expression G. And we partition that we assume that there are p SNPs for the gene G. Then we assume that these p SNPs are clustered into KP groups. And for convenience, we introduce a vector Z for as an indicator vector, with ZK indicate the cluster that SNP-K belongs to. And if we have already known that the cis-SNP-K belongs to cluster G, then its effect size omega K follows from a normal distribution with mean 0 and its effect size equal to this one. And So here, next is a key point. If we have an informative annotation information matrix, for example, in the favor database, we suppose we have M informative annotations, and we denote this annotation information matrix as W. How can we incorporate this informative information matrix into the TVAS framework? And here is our solution. We propose to use a product partition model with covariate, which in short we call it PPMX prior, to help us incorporate this W into this linear regression model. And please keep in mind that since there is an indicator vector and they take discrete values, so this prior is a discrete prior. And suppose that there are 1,000 SNP for a specific gene G, then there are overall 1,000 to the power of 1,000 probabilities they need to assign for this vector Z. And as you can see that the PPMX primarily consists of two parts. The first part is a similarity function G, and the other part is a cohesion function CSG. And what is the role of the similarity function? So let's imagine this case. Suppose that here is our annotation matrix, and for this matrix, each row represents a specific annotation information. For example, the first row represents the epigenetic information, the second row represents the protein function, and etc. And each column represents a specific SNP. And as you can see that the SNPs are well clustered into three clusters, right? And suppose that Z1 and Z2 are two realizations of the vector Z. And it is apparent that we want to assign a greater probability on this Z1 rather than Z2, because for this Z1 we have clusters the first several SNPs into the first cluster, and the middle part and the third part. It looks more likely to the annotation profile, or in other words, if two SNPs have similar annotation information, then we want to regard them from the same cluster, and so this is what the similarity function act as its role. And the next is a cohesion function. Here SJ is a set contains the index to which the SNP key flow contains the index of the JAS cluster. And suppose that now the annotation information matrix looks like this, and apparently all the SNPs forms only one cluster. And suppose that now Z1 and Z2 are two realizations of the vector Z, and we want to give more probability to this Z1, because for this Z1, all the SNPs belongs to only one cluster. And for this Z2, suppose there are 1,000 SNP with homogeneous annotation profile, and we have partitioned them into, for example, 500 clusters. Then by this cohesion function, this Z1, for this Z1, we will have 900 and 1990. This value is much bigger than this value. So by using this cohesion function, we can prevent the situation where almost all the SNPs have homogeneous annotation profiles. We do not want to partition them into too many clusters. We want them together into the same cluster. And so this is the main part of PPMX prior, and the likelihood of the annotation from the prior of the or in other words, from the similarity function, and we can partition the effect size into different clusters, just like what has done in the Tiger model. But here we can use the annotation information to help us partition the effect size into different clusters. And in practice, we use the MCMC algorithm to help us estimate the parameters of interest. And I don't want to get into the details of the MCMC algorithm. And the next straightforward question is that if we have specified a significant gene trait association, we want to ask which annotation plays the most important role in finding such an annotation. Or in other words, we want to do an annotation assignment for each gene trait association. So by calculation, we have derived that the TWS test statistic can be approximated by this value. Here, alpha is the SNP's joint effect size on the trait, or the effect size from the GWAS summary statistics, and omega is the effect size. Omega is the effect size which SNP impose on the gene expression. And as you can see that the TWS statistic can be approximated by this value. So here we propose to use this formula to help us identify which annotation is the most important for each gene trait association, and it is based on a cosine distance. And here is a workflow of our method, and next we use a simulation to illustrate the powerful the performance of our method. And I don't have time to get into the details to the simulation setting, but as you can see from this figure, the purple one represent our method, and we compare our method with other 40 VAS method, and you can see that we can get a larger imputation R square, and we can get a larger test power, and while we can well control the false discovery rate. And next we applied our MET method to each psychiatric disease, and as you can see that the purple one represent our method. Our method can find more significant gene trait associations, or in other words, we can find more disease risking genes in this it trees. And next, we conducted some pathway enrichment analysis to help us next we conducted some pathway enrichment analysis. For example, for schizophrenia, we have found out, for example, 100 significant genes. Then we put these 100 significant genes into the pathway enrichment analysis, and then we find that the most significant pathway is schizophrenia, which is a very good validation of the correctness of our method. And next, we explored some other data sets, such as the EVAS data set and the housekeeping gene results data set to illustrate the correctness of our annotation assignment. And here is our discussion part. In this paper, we propose a PPS model to account for multiple annotation issue, and which jump out the linear assumption between effect size and annotation scores, which is adopted by most of the existing TVAS method. And the PPMX prior post SNPs with similar annotation profiles into the same cluster, and thereby they share the same similar effect size. And we also have derived that the power of TVAS is determined by the angle between the rotated SNP to trait effect size and the SNP to gene to expression effect size. And by using this conclusion, we can assign the most important annotation for each gene trait association. And for the future direction, it might be a promising road to transfer from the tissue-specific data to cell type-specific data to get more accurate results. And thank you very much.
That's
Yeah.
Hello. Hi. Hello. Hello.
Hi, we can hear you. We can hear you good.
Okay, okay. Hello, everyone.
Hi, you can go ahead. Thank you.
Okay, thank you. Hello, everyone. I'm Wu Qing from South China Normal University. Today, I'm very glad to present my research on the technique for survey with sensitive questions. I hope to share my findings with you, and thank you for coming here today. The title of my presentation is Poisson atom count technique with non-compliance. The work was completed in collaboration with Professor Tianguo Liang from Southern University of Science and Technology, Dr. Tang Man Lai and Derek Feng from Hong Kong University of Hong Kong. There are 6 parts here. First, I would like to introduce the research background and the Poisson atom count technique with non-compliance will be presented. The statistical inference, including the parameter estimation and hypothesis test, will be reported, and the simulation and application will be discussed. In the survey with sensitive questions, refusal and providing untruthful answers from respondents are very common in the survey of collecting highly personal or sensitive issues. Accurate data collections and reliable analysis on these issues are desirable. For example, in medical research, we want to investigate the relationship between HIV status and sex exchange. In sociological studies, we are interested in the proportion of people with crime, the proportion of premarital pregnancy, or the induced abortion. For the governments, they want to know the proportion of non-compliance with rules or tax evasion. Unfortunately, all of the questions are sensitive, and it is difficult to get true answers if we ask the questions directly. We would like to propose the statistical models to encourage the truthful answers from respondents, and to propose the reliable statistical inference for the data analysis. In 1984, Miller first proposed the original atom count technique. In the technique, respondents are randomly assigned into two groups, the control group and the treatment group. Respondents in the groups are only asked to report the sum of the questions. In the control group, there are several non-sensitive questions, and the answers are 1 for yes and 0 for no. The respondents only report the sum of the questions. In the treatment group, the answers are also 1 for yes and 0 for no. Besides the same questions in the control group, the sensitive question is added in the end. Respondents also report the sum of all of the questions. For example, if the answer in the treatment group is 2, there are possible two situations. The first is there is 1 yes in the first 3 questions, and yes for the last question. Also, it is possible that there are 2 yes in the first 3 questions, and 0 for the sensitive question. In this way, it is impossible to infer the true sensitive status of the sensitive question, and the privacy is kind of protected. If we want to know the probability of people belonging to the sensitive group, the difference of the sample mean can be used to estimate the probability. Though the SAT can protect the privacy, but it is often criticized by its ceiling effect and floor effect. The ceiling effect is that if the answer is m+1, m here is the number of non-sensitive questions. If the answer in the treatment group is m+1, it means the possession of the sensitive characteristic. The respondents must belong to the sensitive group. In this way, the privacy protection is breached. And the floor effect means that the answer 0 means non-possession of the sensitive characteristic. And some respondents will choose the answer 0 to demonstrate that they are a good people. To overcome the ceiling effect, we proposed a technique called the Poisson atom count technique. In this model, we replace all of the non-sensitive questions by only one question with outcomes following Poisson distribution. For example, we only ask how many times have you traveled to other cities last year? And in treatment group, the sensitive questions is added. For example, in the treatment group, if the answer is 5, there are two possible situations. Maybe he traveled 4 times last year and belonging to the sensitive group. Or maybe he traveled 5 times last year and do not possess the sensitive characteristic. In this way, all of the questions will not leak the privacy, and people will give more truthful answers. In the Poisson atom count technique, the ceiling effect is solved, but the floor effect is not addressed. We use the same technique just to consider the non-compliance to overcome the floor effect. In the control group, we let X be the answer to the non-sensitive question. We assume it follows the Poisson distribution with a known parameter lambda. And in the treatment group, B here is the target, is the answer to the sensitive question. and z equals to and pi is the probability of z equals to 1. It is the target parameter. Here, z equals to 1 means the respondent possesses the sensitive characteristic, and z equals to 0 otherwise. Different from the Poisson atom count technique, we consider the non-compliance. We assume that some respondents with sensitive belonging to the sensitive group will choose the safe answer 0 with a probability theta to project a positive image. Because 0, the answer 0 here means the non-possession of the sensitive issues. We introduce a cheating random variable called C, and the proportion of the state here is the probability of the condition. State here is a conditional probability of z equals to 1, given that the people belonging to the sensitive group. The state here is unknown, and we assume that the conditional probability of z equals to 1, given that respondents belonging to a non-sensitive group, the conditional probability is 0. Based on the assumption, we can have the stochastic representation of the outcomes in the control group and treatment group. We can have the nonparametric estimator for pi and theta. That the difference in mean estimator, sometimes it may fall outside the unit interval from 0 to 1. It doesn't make sense. So to get here, we apply the EM algorithm to calculate the MLE estimator. We introduce R1, ZJ, and XJ as the missing data in the treatment group. Here we use S0 here. S0 here is the number of 0 observations in the treatment group. We use R1 as the number of respondents whose true answers to the sensitive question is 0. And S0 minus R1 is the number of the cheating zeros. That means the number of S0 minus R1 is the number of non-compliance. Applying the EM algorithm, we can have a closed form solution in the M step. And in each step, we calculate the following conditional expectations of the missing data. The conditional expectation of R1, ZJ, and XJ. Here we use the bootstrap method for the confidence interval construction. This can guarantee the confidence intervals lie within the unit interval 0 to 1. And for the regression model, in practice, we wish to explore the relationship between the response variable and the potential explanatory variables. We use the logistic regression for the target parameter pi j, and this is the stochastic representations of the outcomes. Beta here is the coefficients and that we want to know. Also, we use the EM algorithm, but in the M step, we can have the closed form solution for the theta and lambda. But to calculate the MLE of beta, we can only use the following quadratic lower bound algorithm. The QLB algorithm here is applied, the iterative algorithm is applied to calculate the MLE of beta. And in the E step, we can have the closed form solutions. The EM algorithm continues iteratively until the certain convergence criteria are satisfied. In the service, we are interested in the hypothesis testing of whether the sensitive proportion pi is identical to a pre-specified value. Here we use the likelihood ratio test. The asymptotic distribution of the test statistic is the chi-square distribution with degree of freedom being 1. To make the difference between the Poisson SAT and Poisson SAT with non-compliance, we wish to test whether the non-compliance parameter theta is 0. Here we use the likelihood ratio test. The test statistic, T2 is it's a asymptotic distribution. It's a half-to-half mixture of degenerate 0 and chi-square distribution with degrees of freedom being 1. The third test is to test whether the regression coefficients being 0 or not. Also, the likelihood ratio test is employed. We conducted simulations to compare the performance of Poisson SAT and Poisson SAT with non-compliance. First, in table 1, when the sample size being 200, we set the cheating parameter being 20%. We can see that if we do not consider the non-compliance, when the true parameter is greater than it is 15% or larger, the Poisson SAT, the estimate of Poisson SAT is only half of the true parameter. And if the non-compliance is taken into account, the bias is reduced. Even worse, when the cheating parameter goes to 40%. If we do not consider the non-compliance, we can see that the estimate in the Poisson SAT is far from the true estimate. It's far from the true parameter. That also shows that in the survey with sensitive questions, the non-compliance must be considered carefully. If we consider the non-compliance, the bias is reduced. In table 3, the estimates of regression coefficients and other parameters are presented. When the cheating parameter theta being smaller, that for example, theta is 20%, 30%, or 40%. When the sample size is small, for example, the sample size being 200, the bias is very large. But if we increase the sample size to 3,000, the estimate is near to the true parameter. If the cheating parameter theta goes to 50%, 70%, or 90%, the bias is smaller than that of the smaller theta. And for the application, it has been reported that nearly 21% to 36% of automobile insurance claims contain elements of suspected fraud, but fewer than 3% of them are prosecuted. The data in the companies shows that the insurance fraud accounted for nearly 20% of the total compensation paid by insurance companies. In this design, we want to know the proportion of people commit automobile insurance fraud. So we conduct a design in the control group. How many times did you travel to other cities last year? The answers are from 0 to 52, and the corresponding frequencies are reported. In the treatment group, the answers are from 0 to 53, and the frequency of 0 is nearly 2 times of that in the control group. In the answers, in the frequencies, we can see that the times are the number of 0 observations are 2 times. So This is a strong evidence that compliance is existed in the surveys. Applying the Poisson SAT with non-compliance, we have the result that the pi here, the estimate of pi is 22%, and the confidence interval is 70% to 72%. And the parameter estimate of theta is 0.98, it's nearly to 1, and lambda here is 8.34 respectively. Okay, thank you. That's all for my presentation.
Okay, can you hear me?
Yes, I can hear you.
Oh, okay, thank you for your talk. And considering about time constraint, we will cancel the Q&A part. And me myself is the last speaker of our session. And I need to express our thanks to Professor Shilin Li for her invitation for our three. And my name is Zhang Xu, come from South China Normal University. And let me share my screen. Okay, I think you can see my screen now. And the title of my talk today is Modeling and Learning on High-Dimensional Matrix-Variate Synthesis. And here is the work team of our paper. And the first one is my postdoc mentor, Catherine from PolyU, and also Professor Jian Huaguo from BTBU, and Professor K.C. Yuan from Hong Kong U, and Professor Alan Welsh from ANU. And our paper has been online on the Journal of the American Statistical Association. And my talk will consist of the following 6 parts. For the introduction part, let me show you our motivation first. We know that the high-dimensional matrix objects arise in a broad range of applications. And for this complex structural data, our goal is to extract its low-rank approximation. And this low-rank approximation of a matrix-variate is crucial for knowledge discovery based on matrix-valued observations. And in our paper, our first aim is to model a new class of latent low-rank signals. This new signal has the following characteristics. The first one is modeling rationale is natural. And the second one is that our signal structure is more general than the existing ones. And the third is that our signal intensity is more stronger than the existing ones, which can be illustrated from our numerical studies, and we also proved the theoretical guarantees. And the second aim of this paper is to establish the inferential methodology and the theory and the collection of matrix-variate. The 2 points is that the first one, we have the separable covariance structure and the new and this new signal. So this separable covariance structure may empower our estimation. And the second one is that our modeling assumption is more general and it can empower the data applicability. Okay, now let me introduce the 2 data sets that we use in this paper. And the first one is a COVID city image data. We have matrix-variate observations of size 150 times 150 for 714 samples. Each sample is an image like this, and we can see that it's a gray image of the line CT data. And for this data set, we can complete the following tasks. The first one is an image reconstruction task, and this is done by ST hat, which is the estimated signal part from our low-rank signal. And the second one is image classification task. Here we can use the extracted features from the data to conduct the classification based on logistic regression. And the label of this data set is the co-weight and the non-co-weight. And the second data set that we use is the multinational macroeconomic indices data. For this data, we have the matrix-variate of size 14 times 10, where 14 is the number of countries and 10 is the number of the macro indices. We have 72 quarterly data. And for this data set, we can also complete two following tasks. The first one is clustering. We can use the result estimated loading matrix as the covariates to clustering the countries as well as the indices. And the second one, we can also do the matrix reconstruction using the estimated signal part. Now let me introduce our model. Our model starts from the rank decomposition of any matrix. Here, assume that we have matrix variate of times P1 times P2. And for any matrix of rank L, it has this decomposition where U is a matrix of P1 times L and V is a matrix of P2 times L. And for the columns of U and V, which are the P1 dimensional and P2 dimensional, the high dimensional vectors. So we conduct the vector factor model on these basis vectors. So model one is our model, which we call rank decomposition based matrix factor model. And the first one is the rank decomposition, and the second one is a vector factor model. And here, R and C are the factor loading matrices, and A, I dot, B, I dot are the latent fact vectors, and the Ci and Ai are the idiosyncratic error vectors. This model can be rewritten as the matrix form of formula 2 by rewritten A and B as this matrix, and the idiosyncratic error C and eta as the second line. And we take Z as A transpose B. We call it the global latent factor, and E as eta A. We call it the column-wise latent factor, and F equals CB, which is we call it the row-wise latent factor, and E is the noise matrix. So we have this model 2 as the equivalent form of our red fan. Comparing this model with the existing ones, we can see that the model 3 is called beam fan, where it means that its latent structure is a bilinear form, where it can be seen that it seems like that we take the other two linear parts into the noise part. And for the existing model 4, which is called the two-way dynamic fact model, here the latent structure, the three parts, they take the two linear terms as the latent structure and take the bilinear form into the noise part. So we can see that from the comparing with model 3 and model 4, our low rank signal is more general than these two ones. To illustrate this generality of our signals, we use this tensor subspace perspective. And for the bilinear form matrix vector model, we can see that its signal is lying in this tensor subspace, where the basis of this subspace is the size of the matrices of Ri1 outer product Ci2. So this tensor subspace has a dimension of K1 and K2, which is much smaller than the original space of the P1 and P2. For the two-way dynamic fact model, which is model 4, taking the two linear terms as the low rank signal, and its bases are composed of the matrices of R1 outer product, the identity matrix, as well as the identity matrix outer product Ci2. So we can compute its dimension as this one, which is larger, maybe larger than K1 and K2, but is still much smaller than P1 and P2. For ourselves, the model RedFam, its tensor subspace has this form. We can see that the blue one and the green one are bases containing all the bases in BIM5 and two-way that DFM, while our dimension of the tensor subspace is the same as the two-way DFM. So compared to BIM5, our tensor subspace has more information. Well, compared to the two-way DFM, our dimension reduction is the same as that of two-way DFM, but our tensor subspace containing the extra bilinear form information here. Now let me introduce the separable covariance structure of right fan. When we take the A, B, C eta as a Z mean and mutual uncorrelated, and for A and B, we assume that they are uncorrelated among rows, and for C and eta, we assume that they are uncorrelated across columns. Then we can calculate the covariance matrix of VI has this form, and the covariance of UI has this form. Hello, can you hear me?
Yeah.
Yes, now we can.
Okay, thank you. Sorry for the internet. And the sigma C is the column-wise variance covariance matrix. It controls the correlation of different in X. So we have this separable covariance structure, which means that it's a coordinate product of these two covariance matrix. And now let me introduce the estimation part. When we given observations xt from t time points or t independent samples, then the red sum is the model 6. We need this strong factor assumption, which is the column orthogonality of R and C, which takes this P1 and P2 to consider the high dimensionality. Under the separable covariance structure, we have this proposition 1, which we called row-wise second moment. We can calculate that the expectation of xt at C transpose has this form, where the first where this part is a constant. Here is L and the trace of sigma C. So the column space of this row-wise second moment are equivalent with the column space of sigma R. And also we have the sigma R has the equivalent or approximate equivalent column space with the space spanned by the columns of R due to the strong factor assumption. So according to this two results, we can get that we could conduct the eigen decomposition on this M1 height, which is the sample estimation of the ST transpose expectation. When we conduct this eigenvalue decomposition and take the first K1 eigenvectors as the columns of a matrix, and we times the square P1 as the constant corresponding to this constant. So we have R hat as this equation. And similarly, when we have this ST transpose XT, its expectations comes to sigma R, and the outer part is sigma C. So we can take sigma C hat as the square P times the eigen decomposition with the M2 hat, which is the sample version estimation of the column-wise second moment. After we have estimate R and C, we can calculate the least squares estimator for the factor matrices. We use this least square estimations, and by taking derivatives with 2ZT, ET, and FT, we got a system of equations, and the factor scores can be calculated as the equation 10, and we can get the signal part estimation ST, which is used for the matrix reconstruction as equation 11. And let me introduce the reconstruction error comparison. I introduced 3 comparing models before. So we need to compare their reconstruction performance. We use the measurement PSNR here. And where X is the original image and the X hat is the reconstructed image. So by the equation 10 and equation 11, we can calculate that comparing to the beam FAM and the two-way DFM, our model has larger PSNR values than each of them. Or in other words, the denominator of this PSNR is the MSE. So our model has a smaller MSE than beam FAM and the two-way DFM. Okay, now let me introduce our application part. For the first data, the COVID CT data, we can comparing its image reconstruction results with the bilinear form matrix model and the two-way DFM. Also, we compare its reconstruction performance with the autoencoder deep learning methods. And we can see that when we take different number of factors, we have this result where the QMLE is a MLE-based estimation method for the two-way DFM. It's it will take much expensive computational time, and our method get the better result when the factor numbers becomes larger. Well, comparing to the reconstruction results, we can see their time. We can see their computational time. We can see that the QMLE, though this method has better performance at these 3 factor settings, its computational time is not in the same order with the other PCA-based method. And for the CT image classification, we use this CT, FT, and ET as a covariate and build the logistic regression model. Also for the beam FAM and two-way DFM model, for the beam FAM model, we only use this one as the covariate. And for the two-way DFM, we only use the FT and ET as the covariate. So we can see the AOC value of this method. It tells us that with the different number of factors, different low rank structure or the expected factors may have different influence on the classification result. And for the second data, the macroeconomic indices, let us see the reconstruction results. This is a 10-fold CV cross-validation reconstruction proposed. Because this data set, it has much smaller size, so QMLE cannot work sometimes. And our model is the best among all the other methods. Okay, let me show you the discussion part. So we propose a novel low-rank structure for the matrix-variate, and we developed a convenient PCA-based estimation method based on the separable covariance structure of red FAM. And we provide the superiority of the low-rank structure in terms of matrix reconstruction and all the PCA type estimation. So the model building Bayesian network for these three models are the A, B, C, where we can see that we take all the J, F, E into consideration, while BIMFAM only take J into consideration, and the 2ADFM only take the F and E into consideration. And for future work, we can see that for matrix rank decomposition, it can be regarded as a second order CP decomposition. So when we have the tensor data, like this order tensor X, we can postulate the model below to extend the red fam, where X is the CP decomposition, and each basis a vector of the in the CP decomposition, we take a vector factor model structure into it. Okay, that's my research. Thank you.